Okay, today we are very happy to have Soubhik Kumar from Berkeley. He will talk about the classical cosmological ladder physics. It's a very interesting topic. Go ahead.
Yeah, all right. So thanks a lot for the introduction and for having me here, and also thanks a lot for joining. So today I'm very excited to talk about cosmological collider physics, and more specifically, how various classical energy injection processes can give rise to interesting signatures in the context of cosmological collider physics. So this will be primarily based on this work with Xingyan Chen from Harvard Astronomy and Reza Ibadi, who is a student at Maryland. They appeared in this paper. And with that, let me get started. And I should mention, just interrupt me anytime something seems confusing or you have any questions. Okay, so we know that the universe is very, very uniform when we look at the largest of scales. However, by now we also have very concrete evidences that there are inhomogeneities, which are pretty small on larger scales, but then as you zoom into smaller and smaller scales, they grow. So specifically, by looking at the CMB, we have discovered anisotropy patterns on it. We have also discovered these famous filamentary structures in the distribution of galaxies around us. So we know that these inhomogeneities, they exist. And one question you can ask is, what is the microphysical mechanism, or how did these inhomogeneities come about? And in this context, one of the leading paradigms is that of an inflationary era in the very early universe. The point is, during inflation, space-time expanded very, very rapidly. And as it expanded, various quantum mechanical fluctuations, they got stretched to superhorizon scales. And then subsequently they froze in time, and eventually these perturbations, they came inside our horizon. And then they sourced the classical density perturbations that we observed via CMB and large-scale structure. So it is this quantum mechanical generation and the subsequent expansion that can source these perturbations that we are observing. And what is very interesting is that the Hubble scale during inflation, it can be as high as 5 times 10 to the 13 GeV, which means that when we are looking at these density perturbations today, secretly they could have been generated at a scale that is as high as this. And in that sense, these density perturbations, they can serve as late-time fossils which would have probed particle physics operating at these very high scales. So from a particle physics perspective, these energy scales, they're pretty exciting because we do not have any other direct probes of these scales. And as we will show, there are on-shell signatures that you can extract in the context of this inflationary paradigm using these sort of energy scales.
So can I just ask?
Yeah.
So, it used to be not too many years ago, people said it could be up at the gut scale. But, is this really very robust? Can it really not, so these keep improving, right? Because you don't see tensor modes, I think it's the main thing. So is this really, you cannot have, how quickly does this fall off? Like if I wanted to have 10 times this, is it completely ruled out? Can you give us some sense of that?
Right, so it can, I think pushing the Hubble scale upward is much more difficult because normally,
Maybe you stepped on the cord or something, maybe you want to move that out of the way, or I don't know.
Yeah, I think it's just my computer. I'll keep on playing with my keyboard so as to, I think this is just sometimes going to...
Do you need a power thing?
I do have a power thing in my office, I can bring it.
I'll just get one. I'll get one and plug you in so you don't have to do this. Just keep going. But just answer my question.
Yeah, good.
So the power strip.
Right. So it is very hard to push it above the scale because normally what happens is that the tensor perturbations that you predict, they are literally given by Hubble squared over m Planck squared without any other scale in the problem. So from the upper limits on the B modes, you literally get this upper limit on Hubble scale.
Okay.
It is very easy to push it down though. If you have extra fields in the spectrum, even if the Hubble scale was as high as this, it is definitely possible to suppress the tensor to scalar ratio, but it's hard to push it up. So as an upper limit, this is pretty robust. But if you see some Like if you do not see some tensor mode, you cannot for sure say that the Hubble scale is super low. it could still be possible that Hubble is perhaps like, I don't know, 2 times 10 to the 13 GeV, and you
So it's
did not
really
see.
just the total amplitude of
Yeah,
fluctuations.
exactly. Yeah,
Okay.
yeah.
I'll get you a strip. Keep
Okay,
going.
yeah, thanks a lot. Very good. So these are pretty exciting energy scales from particle physics perspective. And the way we eventually probe these density perturbations, one example is the CMB itself. So the idea is that you generate these density perturbations during inflation. Then, at least in the context of single field models, when these perturbations they exit the horizon, they freeze in time. Eventually, they will come inside our horizon and undergo subsequent subhorizon evolution determined by some transfer function, which are something that are exactly known in the context of lambda CDM. So this is a known evolution. And then, by convoluting these two things, you get to predict the temperature anisotropies that you see in the CMB. So what I'll focus on in this talk is basically to say that our observable is the temperature perturbations on the CMB, but we will focus on the case of lambda CDM such that all the properties that you get to extract from studying this is directly related to the properties of the curvature perturbation. Thank you so much. Very good. So that will be our approach. We'll from now on we'll be focusing on various properties of the R, assuming that the evolution is lambda CDM. And the primary observable that we'll be thinking about are various correlation functions of these density perturbations, which through this linear relation would eventually imply some sort of non-trivial correlation functions of temperature fluctuations that you see on the sky. In particular, you can have the R spectrum, which is just a 2-point function. So this will, at the leading order, be a probe of 2-point function of this curvature perturbation R. And then, going forward, you can also compute 3-point function, which is typically called the bispectrum, and that will be probes of 3-point function of R, and you can keep going, but practically beyond 4-point functions, these searches, they do become weak. So for this talk, we'll primarily be focusing on the bispectrum as a probe of these non-trivial correlation functions during inflation.
Can I ask a question here?
Yeah.
Related? So, right, if we're looking for some deviations from, so the zeroth order theory or first order theory is some Gaussian thing with some power law spectrum, right? Mm-hmm. And we're looking for deviations from that. Mm-hmm. I get it. It's very. But now my question is, if I have some weird new physics that modifies the minimal sort of models of inflation, is it clear that I should expect it to show up in the 3-point function rather than the 2-point function?
Very, very, very good question. So I will talk about scenarios in which you would have the leading signature at the bispectrum, and the reason would be it would definitely affect the power spectrum, but it would be an effect that would modify the overall amplitude. So you can always absorb that into your definition of what the normalization is. So the point is, this guy is sensitive to only one scale because of momentum conservation. You are correlating one k-mode with the other k-mode, which are same in magnitude. So there is a bit of a less structure in this. This guy, on the other hand, will be dependent on this entire shape of the triangle. So it will be sensitive on 3 different numbers, which are basically sides of this triangle. So it's definitely possible to have scenarios where the effect on power spectrum is kind of degenerate with a normalization, but the effect on bispectrum is just completely new and very clear-cut. Having said that, I will also discuss scenarios where indeed you would expect the first signatures to appear in the power spectrum itself, because that will be associated with an extra scale which would break the statement that this is sensitive to only a single scale. Okay. Yeah. All right. So I just told you that we will be focusing on these correlation functions because these are the primordial correlators that will eventually lead to temperature perturbation correlation on the CMB. So let me quickly illustrate how we typically compute these correlators. And this is done by the so-called in-informalism in the context of inflation. The basic idea is very simple. It's just a statement that you want to compute these correlation functions at a fixed instant of time. because that is something that will eventually get imprinted on the CMB and we will get to observe it. And because you are trying to evaluate this correlator at a fixed instant of time, you can choose that time point to be the time point at the end of inflation, because by that time all these modes, they have exited the horizon and they have frozen in time. So for this talk, I'll be focusing on, I'll be drawing diagrams like this, where I'll assume that all my correlators are evaluated on the reheating surface, and that is just a fixed time instant that we are choosing for convenience. So with that in mind, the way you can compute this is just very standard. It's just computing a correlation function. So you have to state what you have to say what your state at the very early time is, and then in the Schrodinger picture, for example, you can evolve the state using some unitary operator. You're computing expectation value, so there is also the conjugate of that operator here, and Q is the operator that you are interested in. So for example, if you're interested in 3-point function, Q would literally be product of these 3-point relations. And then your goal is to evaluate this expectation value, so you can do it by going into the interaction picture as we do in field theory. So you can write all the operators in terms of interaction picture fields. You can rewrite this time evolution operator in terms of some time ordered operator, and then because of the conjugation here, you also have some anti-time ordered piece. So this will roughly be the generic structure that we'll have to evaluate these correlators. And once you have this, you can just do the standard weak contractions that we do in field theory, and that will give you the answer you need.
So you are citing this Weinberg book, Cosmology book?
This one is actually a review paper. I mean, it had a very nice review and also new results. But then this is a paper. Yes.
Okay.
Yeah. Okay, good. So all of these things, as I said, they will be evaluated at a fixed instant of time, and that's why my Feynman diagrams will be somewhat different compared to what we normally see. So for example, if I were to draw a propagator of this R, I'll draw it like this instead of drawing a single straight line, and that is just because I'm evaluating this correlation function at a fixed instant of time, and time is flowing vertically on this Feynman diagrams. Similarly, if we were to draw a cubic interaction of R, I'll be drawing some diagram which is like this, where this is the vertex of interest, but once again, we are evaluating these correlation functions at this late time slice, so that's why these diagrams will be appearing in that form.
Can I ask a question just about your formula there? I mean, I feel like I'm missing something here, because there has to be somehow an effect that is turning on an excitation. No? I mean, it looks like your zero is somehow some vacuum at minus t equals minus infinity, and then you're evolving it with an interaction thing, but normally that wouldn't do anything. So I feel like I'm missing something about what you're just the formal expression.
Right, so good. So I am assuming that you're starting with the so-called Bunch-Davies vacuum, so these are vacuum correlations. But then, because you would also have these, so you also have these non-trivial operators here. So one thing, for example, so just to give you a concrete example, let's say this operator is literally 3 copies of R, and your interaction term has a cubic structure.
Yeah.
So what you do is that if you expand the exponential to the leading order, you can set this thing to unity, and then you are left with just a contraction between 3 copies of R from here versus 3 copies of R from the interaction part. So this is just assuming that what is the, starting from the vacuum state, what is the final expectation value of 3R correlator, and that will depend, I mean, that answer is non-zero only to the extent that things can interact in the theory.
So somehow at minus infinity, you have Bunch-Davies is, I understand what it is for free fields, but you're saying you have exactly that even in the interacting theory, and then you're in a way adiabatically turning on this interaction, and it produces some particles.
Right.
And that is the right physical thing. And Weinberg showed that that's the right physical thing.
Right, I mean, so one...
I'll trust it. Okay, thanks. At least I see why it's not trivial. It's not obvious why that's the right thing. It's not totally obvious to me.
Right. So yeah. So we are assuming that in the sense that like we do have a vacuum state of the interacting theory as well when you turn on the interactions.
Yes.
But I mean, perhaps one thing that will be clear as I keep going through the talk is if you were to ask similar questions about perturbations of very massive fields, then you would encounter exponential suppressions in these correlation functions. And that is just a physical statement that if you are trying to produce a Hubble mass particle if you're trying to produce a very heavy particle with only Hubble mass energies, then those things will be suppressed because vacuum fluctuations, they are not enough to give you enough energy.
I guess somehow this thing must be independent of TF, yes? I mean, so,
It is,
right?
yeah.
And so somehow this is really just building up an equilibrium kind of situation in some language, right? I mean, I know the reheating surface picks a particular time slice,
Yeah.
but this formalism is somehow just taking the Bunch-Davies vacuum and turning it into the interacting quote-unquote equilibrium state in the sitter,
Right.
right?
Yeah.
Okay.
And
Okay,
that is
I think I'm happy. I think
Okay,
I'm okay.
okay.
Sorry.
Yeah. No worries. Of course. Yeah. Okay. So these will be our the structure of various correlation functions that we'll evaluate. So with that in mind, let me illustrate the primary observable that I'll keep referring to. And as I said, both the power spectrum and bispectrum, they are useful probes, but bispectrum in some sense would be our leading probe of various interactions in the theory. And that's why let me just define bispectrum in a bit more convenient way that is also used in the literature. So what we do is we take the standard, like these 3-point function that we are interested in. I'm putting a prime here just to ensure that you have momentum conservation. So any momentum conserving delta functions, they are taken away from the correlator. And then to make the entire quantity dimensionless, we divide it by 2 copies of the power spectrum, which are just these 2-point functions, along with some permutations of these various momentum. So this part in the denominator is just purely for convenience. So because of momentum conservation, like because of both translation and rotational invariance, you can show that this entire thing, it depends only on the magnitude of the sides of the triangles that these momentum form. Okay, so the absolute directions, they are not important, it's just the magnitude of the sides that finally survives. So in principle, this is a pretty rich observable because it depends on 3 independent variables. So there is a lot of information in it. And just to quantify the rough going rate of non-Gaussianities, one thing we can do is evaluate this entire function at the so-called equilateral point where all the momenta are set to be equal to each other. And that thing is typically called FNL. And this is like this parameter FNL is just a measure of how Gaussian or how non-Gaussian various correlators are. So again, just to give you an example, if you were to have an order 1 strong interactions, so if you had, for example, a G R cube type cubic interaction with G being order 1 in appropriate units, then it would predict that FNL is as big as 10 to the 4, and that is just coming because of the fact that because of this normalization, we have an extra factor of R in the denominator, and we know R is like 10 to the minus 5 or so, so once you also plug in some order 1 numbers, it turns out that the FNLs you get, they're roughly of this order. So this is just to illustrate that if you had order 1 non-Gaussianities, then these are the kind of FNLs you would have gotten.
Sorry.
Yeah.
Is G a coupling?
G is just a coupling, yes.
Why G is out of Hubble scale?
So
in the unit of Planck scale or?
yeah, so good. So what I'm saying is that you typically have these fluctuations, and the fluctuations, I'm being a bit sloppy here, so what I'm imagining is you have quantum mechanical fluctuations, which are of the order of Hubble. So I'm setting also G to be some Hubble scale quantity. You should definitely write this thing a bit more properly in the sense that so R technically is a dimensionless object. Mm-hmm. So if you want, the more correct thing to write here would be G, which is of the order of Hubble to the 4. But all I'm saying is that assuming all the fluctuations are of order Hubble, G is just a parameter that quantifies the strength.
Okay, that makes sense.
If you were to write it in terms of just inflatons, you could write, for example, a G phi q piece, where G is literally a dimension 1 object with order Hubble strength. So if all the perturbations were like order 1 non-Gaussian, the conclusion is that FNLs would have been pretty big, of the order of 10 to the 4 or so. And in that context, if you look at the data, you would notice that, as is well known, CMB tells us that the primordial perturbations are pretty Gaussian, and that is quantified by this statement that when you look at various shapes of non-Gaussianity, roughly FNL turns out to be ordered 10 or so, with the precise number here depending on what shapes of non-Gaussianity we're looking at. Okay, so things are quite Gaussian as far as CMB is concerned, and then if you ask what kind of precision future experiments would have, the driving factor would be the improvement in statistics, at least. So for example, if a given survey sees n number of modes, then this is the precision with which you can measure FNL, assuming just cosmic variance. So if you plug in this sort of expression for large-scale structure surveys, for example, you would notice that typically they would be able to improve CMB bounds by a factor of 10 or so. It depends again a bit on which particular shape you are thinking about, but this is a useful benchmark to keep in mind. Spheres can also improve this a bit more. Optimistically, you can get to below FNL values below 1 as well. So broadly speaking, compared to the CMB, you might expect an order of magnitude improvement in the context of large-scale structure experiments. But then if you wanted to go even farther, the ultimate frontier in this game would be probing the dark ages of cosmology using 21 centimeter, and that can be sensitive to a huge number of scales. Assuming very optimistic and cosmic variance on the limited sensitivity, you can get to FNL values which are even as small as 10 to the minus 3 or so. But this is, of course, much more futuristic compared to the large-scale structure surveys that are coming up, and we will be getting to these sort of values quite soon. So this is where the experimental landscape lies, and we'll be keeping these sort of numbers in mind as we quantify various sizes of non-Gaussianity.
Can I ask, should I think that the theory with FNL bigger than 1 is in some sense strongly coupled, so that I should worry about, I don't know, 4-point functions, or is it like that, or is this just really some crazy arbitrary normalization I should pay no attention to?
Yeah, good. So it is indeed this normalization aspect. So I would say if
you said it there, 10 to the 4 is actually the size,
exactly.
roughly.
Okay. Yeah. And that is just because you have this extra, so you have 3 factors of R, and you have 4 factors of R in the denominator, so it's just...
And then, so there's a 10 to the minus 4 height.
Exactly.
Okay, I got it. Okay.
Okay, so with that in mind, let me now get into the basic idea behind the cosmological collider physics program. And here the point is that we have been thinking about 3-point functions, but there is a very interesting shape of 3-point function that arises if you have Hubble scale particles produced during inflation. So let's imagine a scenario like this, where you have a particle production event at some point in time during inflation, and then these heavy particles, which I'm showing in red, let's say you produce a pair of them. One of them propagates and it decays into a pair of inflaton fluctuations, which I'm showing by this solid purple line. The other, it could decay into a pair of particles, but it could also mix with one inflaton perturbations with this other leg set on the wave of the inflaton field, which is just a homogeneous quantity, so it does not carry any momentum. So there exist physical processes like this, which would lead to a non-trivial 3-point function. And if you compute this, you notice something that is very interesting. So in particular, if you go to the so-called squeeze limit, in which one of the momenta is much smaller than the other two, so K3 is much smaller than K1, and K1 is approximately equal to K2, so that's the shape of the triangle you are looking at. Then you would find that the 3-point function, it has this very interesting momentum dependent, so it depends on the ratio of the scales. But then this ratio has an exponent which is parameterized by this parameter mu, which depends on the mass of the heavy particle that got produced here. And then if this particle had some spin, you would also see some non-trivial angular dependence, depending on the spin of the particle. So if it's a spin half, you'll see if it's a spin 1, you'll see something. If it's a spin 2, you'll see some different angular dependence. And here theta is just the angle between K1 and K3. So here's the main idea. Let's say you turn on your experiments, and by looking for appropriate templates, you found that this template describes the data pretty well. And then by extracting this parameter mu, and by extracting the angular dependence here, in principle you are sensitive to the mass and the spin of this very heavy particle that got produced during inflation. So what these 3-point functions they are sensitive to is that they are sensitive to pretty direct on-shell physics that could have been operating during inflation. And as I said, the inflationary Hubble scale could be very high. So in principle, this program, it gives you an opportunity to probe super heavy particle physics that is otherwise inaccessible. And because this is pretty similar to doing bump hunting in the context of standard colliders, but then you are just using cosmological observables, so that's why it has been dubbed as cosmological collider physics, and there has been a lot of work on this subject. I'm just referring to a couple of pioneering works, and then there are many interesting follow-ups as well.
So can you measure the decay width of the particle?
Yeah, very good question. So you can. It turns out that if you have, so it's very similar to like this, right? So in fact, I mean, this analogy, you can show that it goes through quite well. So if you put an imaginary part of this mass, just in an analogy to this, what would happen is that you will see an oscillatory piece, but you will also see some extra non-oscillatory piece, or if you want a real index that modifies this 3/2.
Oh, okay.
So yeah, I mean, you can show this by computing widths of these particles in de Sitter, and this can be done very properly. Yeah.
Another question.
Yeah.
Now K1, K2, K3, you take a squid limit K3 much smaller than K1. Is it possible like a K3, K1 are together and K2 in the background?
Yeah. So, sorry, you mean background?
But I thought you are consider 3-point correlation function. Actually, you are obtain 3-point correlation from 4-point correlation with one field go to background field, right? So I'm asking, can K3, K2 is change each other in your diagram?
So you are still looking for 3-point function, but these two switch?
Yeah.
Yeah, that's totally possible. You'll have just a different shape with so the physics idea here is that whatever got produced and decayed to this vertex and whatever decayed to this vertex, there is a time delay between these two vertices, and that time delay eventually leads to these weird scale dependence. So if you replace K2 by K3, this form will be changed, but otherwise the physics will.
You mean okay? I got it. I think got it.
Yeah.
You need this time delay for the two decay. What is?
Yeah, exactly. I'm gonna show that in a bit more explicit form in a few slides. This oscillation, it is just coming from the standard oscillations that massive particle has while propagating through space.
Okay.
Okay, so now if you so I was just telling you that in principle you are sensitive to very heavy physics. However, there are two interesting and important aspects that this program has. First is if you have particles which are much lighter than Hubble, so in this limit, then if you compute this exponent, you would notice that it becomes vanishingly small. And what that tells you is that because this exponent is becoming so small, it is hard to extract the mass of this particle by looking at 3-point functions, because you lose this non-trivial dependence with K3 over K1. This entire thing just goes to unity.
But probably just a convention. If I take m equals to 0, there is a root minus 9 divided by 4. So if I take this square root square of square root. I think you choose the value for I. Why you don't choose the minus I?
Good. So good. So you will have a value 0 that is here. You'll also have an index that is 3
Yeah.
when you choose the other side.
Oh, yeah.
Right?
What about that solution?
Yeah, so that contribution is suppressed just because you are in a regime where K3 is much smaller than
Oh, okay. Oh, you have that solution.
Yeah.
Okay.
Very good question. So I skipped over that, but both terms are there. It's just that that will be suppressed because you are taking the squeeze limit.
Okay, got it.
Yeah. Okay. So this is the case for very small mass. The other limit that you can take is a scenario where the mass is much bigger than Hubble instead. However, in this, if you go through the computation, you'll find that the 3-point function, it picks up an exponential suppression in that limit, and that is physically understandable because you have Hubble scale fluctuations during inflation, and you are trying to produce a particle whose mass is much bigger than Hubble. So you do not have enough energy in the system to produce this particle on shell, and consequently you encounter this exponential suppression. And if you try to plot this, the suppression is pretty severe. So here, for example, I'm showing the FNL mediated by some heavy particle, and you would notice that even when you go from m over Hubble from a value of equal to 1 to something equal to 2, the associated FNL, it can easily drop by an order of magnitude. There is a pi sitting here, and this order of magnitude decrease is of course very significant from an observational perspective. So naively, if you put these two features together, it seems to suggest that cosmological correlator physics operates most efficiently when you are in a narrow window around the Hubble scale during inflation. However, that's not really super ideal if you focus on particle physics mechanisms, because we do have a bunch of interesting heavy physics candidates that could be around 10 to the 14 GeV or so. GUTS, bright-handed neutrinos perhaps, depending on the neutrino mass generation mechanisms. And these scales, they need not be so close to Hubble such that they leave exciting signatures at the cosmological collider. So this is kind of the motivation for the rest of the talk. We will be trying to understand, are there plausible mechanisms that can excite particles whose masses are not necessarily directly around Hubble. For example, if a particle is 10 times heavier than inflationary Hubble scale, can it still lead to something that is observable? And in this direction, we have seen quite a lot of recent interesting works, including something that we worked on in the context of exciting charged scalar particles with some U1 symmetry. In this talk, however, I'll be focusing on real scalar particles, and the reason is that we'll need something qualitatively different from the existing mechanisms, because all the existing mechanisms, they rely on a chemical potential-like structure, which is basically just another term for current coupling of the inflaton. So, in other words, what the existing work have been focusing on is a derivative coupling of the inflaton to currents of various heavy particles. So either currents you make with charged scalars, or currents of fermions, or Chern-Simons terms for gauge bosons, and so on. But all of these current couplings, they do not directly exist for real scalars. So that's why we want to investigate what kind of other mechanisms you can have such that you get to excite super Hubble masses, and whether they can lead to an observable signal. Okay. So that's roughly the goal of the talk, and I'll broadly talk about a couple of different mechanisms, primarily focusing on the mechanism shown on the left part of the figure here. So what I'll imagine is that I'll get into the microscopic physics in a bit more detail later, but what I'll imagine is that during inflation, you have an oscillatory source that could be oscillations of another massive particle or oscillations of the inflaton itself, but you at least have this source which is parameterized by a frequency omega c. And this source is the one that provides enough energy into the system so that you can produce an inflaton quantum and a heavy particle quantum. So this source is the one that is responsible for avoiding these Boltzmann suppression that I was talking about. And then once you produce this heavy particle, it can go and it can decay into a pair of inflaton quanta, and then it can give rise to the standard cosmological collider signatures that I have been talking about so far. But the crucial difference compared to previous sets of scenarios is the existence of this classical clock field, and I'll be getting into more detail what actually I mean by such a field. But there is, the important takeaway here is that we will have an extra source of energy injection that will help us produce these otherwise Boltzmann suppressed particles.
Do you need omega speed to be comparable to your lab?
Exactly. So I'm gonna come to that. So yeah, absolutely. Yes. The other set of mechanisms that I'll be talking briefly about is if you have some non-trivial feature on the inflaton potential, then that feature could have also extra energy scales or super Hubble energy scales, and those energy scales can again excite very heavy particles. So we'll model such an energy injection in terms of a step function, but more generally, anytime you have some sort of a sharp feature on the inflaton potential, the inflaton would experience a large kick while passing through that part of the field space, and as a result, that kick can excite heavy particles as well. Okay, so broadly speaking, for both the cases, you have extra sources which inject energy, and it lets you produce these heavy particles which are otherwise super suppressed. Okay, so with that, let me get to the rest of the talk. So I'll, again, as I said, primarily be focusing on the case of oscillatory features. Then I'll briefly talk about the case of sharp features, and then I'll also give some quick examples of how these oscillatory features can arise from the context of an inflaton potential or from the existence of other classical fields in the spectrum. Okay. So this is how I'll be parametrizing the relevant interactions between the inflaton and the other heavy field. So I'll have a piece that involves only the inflaton. And this piece is, I'll just assume that it satisfies slow roll at the leading order. So, just a standard picture. We will talk about a scenario in which the inflaton potential would have some oscillatory features. So there, this part, the inflaton Lagrangian, would be somewhat modified. There will also be this Lagrangian of the massive field chi, which we want to excite and observe through the cosmological collider. So this is just a standard Lagrangian involving some kinetic and potential term, nothing important or non-trivial here. And then the important bit would be encoded in this interaction term that couples the inflaton with the massive field. And I'll impose a shift symmetry on phi just to make sure that it remains light in the face of radiative corrections. So I'll be having derivatives acting on the inflaton that imposes this shift symmetry. And with all of that, we can now get into a bit more detail of how these interaction terms work. So I'll do a very simple parametrization for the time being, and then later on, I'll give a more concrete example regarding how these interactions can arise. So I'll start with a quadratic mixing, where delta phi is the fluctuation of the inflaton and delta chi is the fluctuation of the massive field that we want to observe.
Sorry, this phi, this chi field is a boson?
Chi field is a boson, yes.
Okay.
Yeah. In particular, it's a real scalar field for our purpose.
Okay.
So it does not even have any charge. Yeah. Okay, so I have this non-trivial kinetic mixing type term here, and the reason why you can write such a term is because Lorentz invariance is spontaneously broken during inflation, so you can have such a term in your Lagrangian. And as I said, I'll be showing how these terms can arise from a more Lorentz invariant description in the UV. But for now, let me stick with this term. And then what I'll assume is that this term has a coefficient which has a time independent part, which I'm parameterizing by rho, and also a time dependent part, which I'll parameterize by a function b of t. And this time dependence is the primary source that will inject energy into the system to produce the heavy chi particle. So this will be our primary focus of interest, and I'll keep coming back to it depending on what form this b of t parameter has. And then I'll also have some cubic interactions between the inflaton and the massive field. This term is just the inflaton kinetic term written in terms of temporal and spatial derivatives, and delta chi is again just a fluctuation. And there is a dimension 5 operator, so it's suppressed by some scale lambda. Little lambda would be just some order 1 parameter. And once again, in principle, you can have a time-dependent coefficient here as well. But for our phenomenology, this would only give rise to some subleading effect, so I'm not going to consider that.
So if I was trying to write, starting with some Lorentz invariant theory, that mixing term, I might think it comes from some d mu phi chi type term, and then
exactly.
d mu phi is non-zero,
Yes.
but my point is that it's small, it's suppressed by some epsilon or whatever in inflation, right?
Right.
So I mean, is it, on the other hand, you may have more freedom if you're really just writing the effective theory of inflation. You have much more freedom and you don't know. Do you have to make use of that freedom to get a big enough effect?
Yeah, very good question. So in the end, when I'll be talking about numbers, I'll assume that these parameters, they are inherited from a UV description. So we'll be a bit more conservative in assigning how big these contributions will be.
Okay.
On the other hand, as you said, if you take a pure EFT of inflation approach, then you can definitely make the rho appropriate.
But you're going to find interesting effects even for sort of regular models that have some, UV models that are valid above the scale of inflation, above the Hubble. Okay, thanks.
In some sense, there is an observational implication that you can still have, focusing on purely EFT of inflation approaches, because if you draw a propagator, you notice like this mixing would correct the inflaton power spectrum. So from that, you will have some restriction on rho purely on observational grounds. So, and in the end, that is the restriction that we'll put in, and we'll see that it is in some sense more. It depends on what your scale is, but let me get into that when I talk about explicit implementations. Okay, so this will be my interaction Lagrangian, and then what we now want to do is to compute these inflationary 3-point functions in the presence of all of these interactions. So once again, this is the init expression that I had from before. So this is the observable of interest. You have 3 copies of delta phi that you want to know the correlation function of them at some time towards the end of inflation. And then you have this time evolution operator and its conjugate to evaluate the expectation value. Now, depending on what part of the interaction vertex, like where it is coming from, whether it's coming from the time ordered piece or the anti-time ordered piece, I'll just, for notational convenience, denote them with plus and minus respectively. In other words, when I'll be talking about plus minus class of diagrams, what I'll really mean is that the cubic vertex, it comes from the time ordered piece. On the other hand, the quadratic vertex, it comes from the anti-time ordered piece. This is just purely a notational convenience to organize various diagrams that appear. You can of course have the thing the other way, where this comes from the time ordered piece and this comes from the anti-time ordered piece, and that would be a minus plus diagram, but that would literally be just the complex conjugate of this one. So that does not give you any new information. And then of course you have the more Minkowski-like diagrams where everything comes from, let's say, the time ordered piece. So you basically set this entire quantity to unity, and you have both the vertices coming from the time ordered piece. So this is what we normally do when we compute amplitudes. So there it is important at what times, or the relative time ordering between different vertices. So you can have one contribution where the 2-point function takes place earlier compared to the 3-point, you can also have them swapped, and those will have different physical implications that I'm going to mention. So I'll call these to be plus-plus type diagram, and once again, you can have their complex conjugate, where both the vertices come from this piece, but that does not give you any new information.
So I should be thinking of this Lagrangian here with these B's and C's as some pretty general parameterization of the 2-point and 3-point mixing, right? So
Right.
for now, that's right.
Yeah.
Okay.
Yeah, absolutely.
Okay.
Okay, so these are the different classes of diagrams we have, and let me now get into a bit more detail about how these contributions behave. So let's focus on the plus-minus bit. So as I said, in this case, you have these two vertices. They come from, like, one of them comes from here, the other comes from here. So you get to factorize these time integrals completely. So you do not have any nested time integrals that we would have normally seen in Minkowski computations. So as a result, the computation becomes a bit more simple. But before getting into that, we can already see one aspect of this factorization, which is that you basically get to chop this diagram into two pieces. One piece is just the question of what is the amplitude of production of one inflaton quanta and one heavy quanta in the presence of energy injection. And the other part, which is literally multiplying this physical process, is the question of what is the amplitude that you can produce a heavy quanta and two inflaton quanta starting purely from vacuum without any energy injection. And as you can expect, because this is a massive particle with mass much larger than Hubble, you do not have enough energy injection if you start with the vacuum, and this sub-process, it becomes exponentially suppressed if you go through the computation, and also that is what you expect physically. On the other hand, this bit, because of the energy injection, you can actually produce this without any suppression, but then of course the entire diagram would still inherit the exponential suppression coming from this sub-process, and that is something that will make this entire plus-minus contribution to be exponentially negligible. So you can show that more explicitly by plugging in all the de Sitter mode functions, but I'm not going to go into more details of that. Yes?
I think I haven't understood something. Why, somehow, I don't understand, why did these contributions appear here but not in the other case? Is it because you're assuming these functions B of t and C of t are still turned on? I don't understand why these contributions aren't also, why contributions like this aren't also, namely, whether one perturbation coming from each side, why those are not there in the standard approach. Can you remind me of that?
By standard approach, you mean without
in the thing that you reviewed at the beginning, the standard cosmological code.
Okay. Yeah, so in that case, you do not have this energy injection.
And why you only have energy injection on one side?
Good. So that's, yeah. So
That's
sorry
all
for.
I just would like to understand.
Yeah. Good. So no, that's a bit of a confusion due to the notation itself. So you will definitely have a process. So just to quickly answer your questions, for the rest of the talk, I'm going to switch off the C of t term, because we'll see that if it is present, it's going to lead to extra contributions, but that are going to be subdominant compared to the 3-point functions that will already compute. So I'm gonna switch off this term,
Fine.
and that is why all my 3-point function is just going to have a vacuum production. So there is not going to be any energy injection that comes through this vertex. So that's just a choice. And then if you ask what happened with the earlier literature, there the point is that in those cases you did not have either of these two energy injections. So there you are only looking at vacuum fluctuations, if you want.
Okay, I think I just haven't understood something even more basic. It's just why is B on the top of the diagram?
The
The other thing is on the bottom.
Okay.
It's just maybe something very basic.
No. Sorry, I should have clarified. So this is just this notation that I'm drawing all my anti-time ordering on the.
Oh, that's right. They're both, but it's just, but somehow that contribution wasn't. The contribution, so it could actually come from either, sorry, because you've written the other ones, but why in the standard case they didn't have these contributions? Did you say that, or?
Yeah, so in the standard case, you'd have exactly this diagram, except for any energy injection coming from here.
Oh, I understand. It's just that the energy couldn't be conserved at that vertex, so that, I got it.
Yeah.
Got it. Okay, thank you, sorry.
Okay, no, yeah, thanks for clarification. So again, just to repeat, just for notational convenience, I'm gonna draw all the anti-time ordering pieces on the top of this line and all the time ordering pieces below this line. And just a notation, nothing important physically is going on. Okay, very good. So I was just telling you that the plus minus piece is exponentially suppressed because you do not inject energy through this vertex. So now let's look at the two parts of the plus-plus contribution. One part, so here, because both the vertices, they're coming from some time-ordered operator, the relative time points where these vertices happen, that is important. So let's consider this case where you have first a production of a heavy quanta and two inflaton quanta, and then this heavy quanta, it travels in time, and then it mixes with an inflaton quanta, and then that gives you the final correlator. However, as expected from before, you do not have enough energy injection in this vertex, so that is why it is difficult to produce this particle on shell through just this vacuum production. You can definitely make this line off shell so that it is not propagating as much in space-time, but it's just a contact interaction. So that is going to give you Hubble square over m square suppression, exactly as in flat space-time. But such a vertex won't have these non-trivial cosmological collider-like momentum dependence because that vertex does not have a long time propagation of these heavy quanta. So in other words, if you want to extract these non-trivial momentum dependence, that piece is going to be exponentially suppressed because of lack of energy injection, and you are only going to be left with a less suppressed EFT type contribution, which has a going rate of 1 over n squared. And then there is the last remaining bit, which is the situation where the 2-point function happens earlier, and then you have the 3-point function taking place. So here, this is much easier to understand physically because what you are saying is that you have an energy injection into the system, and then that produces the inflaton quanta and the heavy quanta. The heavy quanta propagates in time on shell, so it can literally oscillate as a function of time, and then eventually it can decay into a pair of inflaton quanta and give rise to this non-trivial 3-point function. So because of the energy injection, you have this on-shell production, and that's why this correlation function will be the one that will encode the interesting cosmological collider signal. So because of that, let me get into a bit more detail of how, what kind of momentum dependence you would expect in the context of this process. So you can do a stationary phase light estimate or local energy conservation if you want to estimate various momentum dependence. So first let's focus on the vertex, which is the 2-point vertex. So what's happening here is that you are injecting an energy, which is omega c, and I'm going to parameterize everything via mu c, which is just omega c in units of Hubble. So for our interest, mu c will typically always be much larger than 1, just to illustrate the non-trivial physics. So you have this energy injection, and then through this energy injection, you produce an inflaton quantum, which has an energy which is given by k3 times eta 2. K3 is the co-moving momenta, so this entire combination is the physical momentum. And then you also produce this heavy quanta, which has some momenta, along with some rest mass, which I'm parameterizing by mu. So this is literally energy conservation applied at eta 2. And you can solve this to derive what eta 2 is as a function of mu c, and the momentum of interest, which is k3. So what this is telling us is that given mu c, there is a preferred time in space-time where this particle production would happen, where you produce this guy and this guy. And then after you produce the heavy quanta, there is a second instant of time where this quanta can decay into a pair of inflatons. And that time instant you can also compute by applying energy conservation. So this is the energy that the heavy particle is injecting into the system at this vertex. And this is the total energy of the inflaton quanta. So here K12 is literally the scalar sum of K1 and K2. So this is the total energy that the two inflatons has, and this is the incoming energy that the heavy particle produces. So from this again you can compute what this time instant is in terms of the other parameters. So I'll also be using this variable p from now on, which is just the ratio of K1 plus K2, entire thing divided by K3. So just to summarize, what I'm doing on this slide is just applying stationary phase or energy conservation to compute the time instants where these particle productions would happen.
Sorry, I'm a little bit confused about the convention. So, the eta is the time, is the conformal time?
Eta is the conformal time.
Okay.
Yeah.
Mu is the frequency in terms of Hubble. Okay, I just got it. Okay.
Yeah. Yeah.
They're both dimensionless, K
That's
eta
right.
and mu.
That's
Yeah.
right.
Okay.
So using these time stamps, you can now compute the kind of momentum dependence you would expect for the 3-point function. So there are two parts of it. One part is just the oscillation of the source itself. So I have been telling you that the source oscillates with a frequency omega c, or when you write it in terms of Hubble, that is just mu c. And that oscillation, starting from some conformal time eta naught, ending at eta 2, is just given by this quantity. If you write it in terms of physical time, this is literally e to the plus minus I mu c times t0 minus t2. It's just that. It appears a bit funny because I've written it in terms of conformal time. And then if you can rewrite this time dependence in terms of the momentum modes that exit the horizon at these times. So if I write K0, if I have K0 to be the mode that exits at eta naught, then by definition K0 times eta naught is order 1, so you get to replace eta naught by 1 over K0. And you can do the same thing with eta naught, where you solve the energy conservation equation from the previous slide to plug it in terms of K3. Okay, so just applying that algebra, you would arrive at something like this. So this is for the oscillation of the source, but then you also have the oscillation of the heavy particle, and that happens from eta 2 to eta 1. So once again, you can write that in this way. This is just again e to the I m times t, written just in terms of conformal time, and you can also rewrite in terms of momentum in this way. Okay, so these two pieces, they would constitute the final momentum dependence of the entire answer, which comes out to be something of this kind, where this piece comes from oscillation of the source, and this piece comes from the oscillation of the massive particle, and this is the piece that you would be interested in because you are interested in extracting this number mu from the perspective of cosmological quantum physics.
Sorry, what is Kr? Much smaller than K3, much smaller than K1. What's Kr?
Sorry, good. I did not write this explicitly. So Kr is literally this combination, K0 times mu c.
K0 times the mu c.
Yeah, thanks for
Okay.
asking. Yeah. Okay, so with this physics picture in mind, we can now get into a bit more details of the computation. I mean, just to illustrate how things are done. So, in the squeeze limit, you can actually compute this so-called plus-plus contribution. The vertices that I was talking about, these two vertices, it turns out that in the squeeze limit, they are sufficiently separated so that you can simplify the associated Feynman propagator if you want, and these two time integrals, you can factorize them. I won't be going over all the details, but we do this in more detail in our paper. And this is the answer that you get. So the 3-point function coming from this plus plus bit, it has this momentum dependence that I was motivating about. So you can reproduce that from these more involved computations, along with some non-trivial mass dependence that comes out. So we could compute this prefactor that is dependent on mu and mu c. It appears a bit long, but then you can take some simple limits to convince yourself that this is exactly the physics you expect. Namely, if you focus on scenarios where mu is much bigger than mu c, you can show that this coefficient, it has this exponential suppression. And this is again just a simple statement that if your mass is bigger than mu c, you again do not have enough energy injection into the system, so the answer gets exponentially suppressed. Okay? So roughly speaking, this is as much you can do analytically in terms of estimating these signals. But then if you move away from the squeeze limit, it's very hard to do these computations analytically, and you have to do all of these integrations numerically. So that's something we do in our paper. But I won't bore you with all the details. We just sum all of these contributions and do the appropriate numerical integrals. And here's the final result that we have. So what I'm plotting is the 3-point function as a function of these shape dependence, where I'm plotting the ratio of k1 plus k2 over k3. So you'd recall that here I was talking about these sort of oscillations. So I have gone to the squeeze limit, so k1 is same as k2. So I have just omitted writing k2 explicitly. But this is the kind of oscillations you would expect. So if you write it in a more familiar form, this would literally be a sinusoid with an argument of mu times the log of this ratio. So this is exactly what you see through the numerical and analytical computations. So I'm plotting these 3-point functions as a function of this ratio, as I said, and I have these two cases. The details are not super important, but just to give you a quick idea, n equals 0 is a scenario where this oscillatory source that I have been talking about, that does not dilute as a function of time. So I'll give an example of the 3/2, and this is a scenario where the source dilutes as a function of time. So once again, I'll give a concrete example later on. But for now, you can just imagine them to be two different physics cases. But for both of these cases, you would notice that the numerical results that are shown with these dotted points, they match quite well with the analytical computation in the squeeze limit, which are shown by these green lines.
Just a quick reminder, you ran out of time, but you can wrap up in 10 minutes.
Yeah, of course, yes, definitely. You notice that there is a bit of a mismatch in for the n equals 3/2 case, and that is just because in this case the source dilutes as a function of time and it has a finite duration, whereas for our analytical computation we assume that the source persists for much longer. So there is a bit of a mismatch here, but in this case, as you expect, the match is pretty good. Okay, so this was the main physics aspect I wanted to illustrate. And then for the rest of the talk, I'm just going to quickly mention some of the other example scenarios, namely what we can have with sharp features. And then I'm going to give a couple of quick examples of microphysically how these B and C parameters can arise. Okay, so let us now go back to these Lagrangian that we started with. And so far, we have been thinking about B of t, which oscillates in time. But then, just for a separate physics case, you can also consider a situation where B of t changes sharply as a function of time. And the physical picture you can have in mind is, suppose inflaton is moving along its landscape, and then at some point it undergoes, like some other field undergoes some sort of a phase transition as the inflaton moves. And that phase transition could cause an energy injection into the system. So I'm just parameterizing that with a theta function. You can also have directly some sort of a sharp feature for example, something that could happen in the context of hybrid inflation models. So that would affect the inflationary potential directly. And again, just as a cartoon way of motivating that, I'm considering a theta function here. But the rest of the physics points, they are all same as before. In particular, if you focus on a theta function, you would notice that if you just Fourier transform it, you have support from arbitrarily large frequencies. But of course, higher frequencies would be suppressed in terms of amplitude. But otherwise, in principle, this is also a mechanism with which you can inject energy into the system. And then again, you can repeat the similar sort of computations, both analytically and numerically, and we do find a good match between the various estimates. And once again, these are the desired oscillations that you are looking for, and you are always trying to extract these parameters from these oscillations. So this was just to give a quick example of another type of beam. And then in the remaining few minutes, let me give you a couple of examples in which I explain how you can have such a B of t to begin with from a microphysical perspective. So let me now specify a Lorentz invariant EFT which couples the inflaton to the massive field of interest, which is chi, along with some other field that let's say, just oscillates with time. So this is a field that is important, but this is not the field we are trying to observe. But I'll show you in a moment why this can be also important. But roughly speaking, you impose a derivative, you impose a shift symmetry on the inflaton. So you impose this derivative interaction, and you can write things at the order of dimension 5, then dimension 6, and so on. So there are a bunch of restrictions that this EFT would have. I briefly talked about this because of Marcus's question earlier. So if you set one of the inflaton to its valve, this would exactly give you the B of t interaction that I was talking about, because you will have a phi 0 dot times a del phi dot times chi, and that phi 0 dot piece would contribute to a power spectrum. So you have to require that this scale is sufficiently large so that you do not give a large contribution to the power spectrum. So that's this restriction. And then same is also true for this sigma field. And you can put a restriction on lambda sigma as well. There is also another restriction that comes from demanding good EFT control of the theory. So because of shift symmetry of the inflaton, you can write arbitrary powers of this dimensionless quantity in your EFT expansion. And if this quantity is larger than 1, that would basically mean that your expansion is not in control. Therefore, you have to, whenever you set phi to its background value, you have to put this condition, because that would ensure that subsequent powers of this quantity, they are increasingly smaller and smaller. So just to summarize, you have these restrictions just from observational and EFT grounds on these coefficients, on these cutoff scales lambda chi and lambda sigma. And these bounds will be important when I'm going to show you the final numbers. So before getting into that, let me just give you these couple of examples of how B and this B of t parameter can appear. So one concrete example you can have in mind is when the inflaton potential itself has an oscillatory feature on top of it. So this is pretty exaggerated because I have said that the corrections, these oscillatory corrections, they are 10%. Current observational constraints are actually more stronger than this. But this is just to show you visually how it would appear. And what happens is that if you have these oscillatory inflaton potentials, as the inflaton rolls on this potential, along with a slowly rolling piece, it would also pick up a subdominant but an oscillatory piece, which I'm denoting by phi 1 of t. So you can show that this phi 1, it is indeed something that can oscillate with time, where this frequency omega c, it depends on the frequency with which the potential varies. So the summary is that because of these oscillations, you have these subdominant oscillations of the inflaton itself. And then if you go back to this dimension 5 operator, you can set one of the inflatons to its background, but then along with this homogeneous piece, you also have this subdominant oscillatory piece. But this is something that has high frequency in it. So this finally gives you this non-trivial B of t parameter that I was talking about. So in this case, you would exactly have what you need, some oscillatory piece that multiplies this quadratic interaction, and then there will of course be the standard cubic interaction. So this is one example in which you can have oscillatory injections, oscillatory energy injections into the system. The other option is that this other field sigma that we had here, this sigma itself could be oscillating in time, and as it does that, it can also inject energy into the system. So for that purpose, we can focus on this dimension 6 piece. So let's do that. So I'm assuming that sigma is just, if you want, it's a very heavy action-like particle that is not in the misaligned regime, but rather it is something that is oscillating as the universe is evolving. And if you use that notion, then this dimension 6 operator would give you an extra source of energy injection because you can set this sigma to this oscillatory background.
So, are you assuming any interaction between sigma, chi, and phi and the standard model particles?
I'm not specifying what the standard model is doing because I'll just assume that, they do couple to the inflaton, but that is just in the details of reheating.
Okay, you mean they are not coupled to sigma and chi?
Right, they're not coupled to it, I mean, that's also separately interesting, of course, but
okay.
I'm not going to focus on that.
Yeah, because if you have a more field, I'm not sure if there's as a curvature perturbation bound, if you have a more source of this fluctuation, quantum fluctuation, you will have some as a curvature mode. It's broadly constrained by.
Right. So that can definitely happen. So that's why I have been focusing on a scenario where everything eventually comes from the, let's say, the
Y thing. That's fine. Okay.
Okay. So again, this is this other example where you get an oscillatory B of t because of this oscillatory signal fields. Okay, so as my final slide, so let me just summarize the numbers for FNL that we get as a function of this heavy particle mass. So I'm plotting a bunch of contours here for a bunch of curves here for various values of omega c in units of Hubble. And as you expect, if you, for example, focus on this example, where omega c is 60 times Hubble, you notice that you can produce all heavy particles up to the scale omega c, again as expected, but then beyond that scale you do incur a very heavy exponential suppression, so the production mechanisms get cut off. But then, if you look at these numbers, you'd notice that these associated FNLs, which are again computed by respecting the EFT bounds and the power spectrum bounds, they can indeed be ranging from order 1 till order 10. So these are some targets that is relevant for upcoming LSS missions. And just to reiterate again, what these energy injections, what they have done is that they have basically extended the reach of the cosmological collider, which would be basically lying somewhere here, very close to the Hubble scale, to something that can be much, much bigger than Hubble. So in principle, you can excite the heavy fields of interest that you have in mind in the context of some high-scale mechanisms. Okay, so this is just to summarize again. We have these two classes of energy injections into the source. And with that, let me conclude. So we definitely have very motivated high-scale models involving GUTS or right-handed neutrinos. But these scales could very easily be much larger than 10 to the 14 GeV or much larger than the Hubble scale. So that is why it's worth exploring inflationary mechanisms in which these fields, they can also give signatures in the cosmological collider. And we have described one such mechanism that is applicable for real scalar fields. This can also work for fields with non-trivial spins, but that is something we have not thought carefully about, but it is definitely worth thinking more about. And then focusing on such a scenario, we have shown that you can excite heavy particles which are 10 or 100 times larger than Hubble, and they can give rise to observable signatures. So yeah, with that I'm concluding here, and thanks a lot for your attention and questions.
Thank you. Any questions? Oh, you want to go on?
Yeah.
Go ahead.
So if you work under a different inflation model, you just change the B of t?
Yeah, so indeed, so it depends a bit on the scenario. So if you work in the case where this V of phi does not have any oscillatory features as well, then the ingredient that you need is this extra scalar fields. You need something that is oscillating as a function of time. So in that sense, yeah, that is choosing some specific function for B of t. But on the other hand, if your potential already has these oscillatory features, as for example can happen if you have action inflation models, then that already determines a B of t, because you do not need any other extra fields to exist in the spectrum.
So is the final result sensitive enough to eliminate some inflation model now?
Yeah, I mean that's much harder. I think I mean in the end, what you mostly care about is how much energy or what is the value of omega c that you had in the system. It's very hard to reconstruct the inflationary mechanism just from observing these correlation functions. Yeah.
I mean, I think my executive summary of this, tell me if you agree with this. So in the conventional case, what I have is a kind of equilibrium situation. I might have some heavy particles that interact, and they deform the sort of equilibrium de Sitter three-point function that then imprints itself on the final state thing. Now there, particles that are heavier than the Hubble are Boltzmann suppressed, they're exponentially suppressed. So here you've added a oscillatory source, and so the freshman physics of that is that you have some sort of, you have some heavy particle, which is like a swing, and it's heavy, but you're exciting it by a lower frequency source, so that's like pumping a spring off a swing or a spring off resonance. And of course you pay a price for that, but it's only a power law, right? When you're off resonance, you don't lose the efficiency doesn't go down exponentially, it just goes off like a power law, so you're able to get, right? So you have to believe that there's some new source of oscillations, but then you are able to probe heavier particles. Is that
right? Right. So I add one more thing to that, in the sense that we can excite this swing on resonance as well, because if you for example injecting this omega c amount of energy through this energy conservation process, it's definitely possible to produce these guys on shell.
Right, but I thought you were more interested in extending the reach to heavier particles, but yes, that... Right,
so indeed, so in some sense, just to summarize again, to go back to this plot, let's focus on this piece. So if your masses are below this, you can produce all of these on resonance, but then if you are above this, then you are off resonance, and then you pay the EFT price.
I see, right, because you also have, because this is a swing in a viscous medium, and so once you, okay. So there's sort of a compromise, there's still this damping that's trying to get rid of them, so it's kind of like a damped, it's kind of a damped oscillator, and now you're going into the...
If you keep moving, if you have masses which are larger than omega c, that's where you pay the price, that is not an on-shell object.
But is it literally the overdamped case of a driven harmonic oscillator, or is it different?
I'd say it's just a regular oscillator if things are getting produced on shell.
Yeah.
The only damping you have, if you want, is the Hubble damping, because things are getting diluted as a function of time. Other than that, it doesn't encounter anything else.
Okay.
Yeah.
Okay, thanks.
Question? If there are no question, I thank the speaker again.
Thank you.